Hi everyone. I'm Ivanna. I'm a second-year PhD student at ISO Garching. I'm supervised by Gerge Popping, Michele Ginolfi, and Nicolas Boucher. So first, I'd like to thank the organizers to give me this opportunity to share my work with you. Also, it's the first time I'm actually sharing ALMA work. So far I was working with Muse and Extruder, so I'm happy that the first time I'm sharing this work is within this conference. I would also like to thank anyone who made the effort to wake up early for this talk, because it's also early for me. So today I'm going to tell you about this HST dark galaxy merger that was revealed by ALMA. So it's unfortunate that this title spoils the outcome of the story, but the story itself is still very interesting. And I'm going to call this galaxy merger throughout this talk Matilda. And that's because I mostly studied and discovered this merger while I was observing at Apex in Chile. And this is where I met this famous Apex Basecamp member. So you guessed it, this famous member is called Matilda. That's why I'm calling this system Matilda. So first, to give you some context before I dive into the topic, my project, one of the two main pathways through which galaxies evolve is via mergers. So when at least two galaxies collide, and here I'm showing you a beautiful example where you see two galaxies dancing together, if you want to say it in a more poetic way. And this phenomenon plays a key role in the evolution of galaxies and the buildup of their baryonic properties like the stellar mass. And therefore, it is crucial to better understand the impact of such systems, galaxy mergers, on the mass assembly of galaxies at different epochs in the universe. And so in the next slide comes a famous plot that you have seen many, many times if you work on galaxies. And if you don't, and you follow the talks of this week, you've at least seen it once. So maybe you guessed it, this is the plot. So this is the famous plot of the history of cosmic star formation through cosmic time. And so you see that the cosmic star formation rate peaks at a redshift of around 2. So this is what we commonly call the cosmic noon. And now we can ask ourselves how much of this cosmic star formation is impacted or contributed by galaxy mergers, and in particular, major mergers. So when we have galaxies of similar masses. So now what I'm showing on the right is the fraction of major mergers as a function of redshift. And you see that this fraction of major mergers increases with redshift. And today I'm going to focus on a particular system at redshift 1.17, so right after the peak of star formation rate that I showed on the left, and where, according to this plot, we expect the fraction of major mergers to make up about 20% of galaxies. And finally, on this slide, one very important aspect to take into account when we talk about galaxy mergers, and in particular the fraction of major mergers, is how do we classify galaxies as merger in the first place? And one common way people have been using to classify galaxies as mergers is through the visual inspection of rest frame optical and near-infrared data. So the key point here that we need to understand is that with this method, if we want to classify galaxies as galaxy mergers, we need to see all the components that make up the system. And so here I'm showing you an example of HST and Muse data, where you see that this merger is nicely identified with the two circles at the center. And today I'm presenting you one clear example where this method can't work alone. And so to give you some background story, I wasn't looking for systems such as Matilda. I was originally working on a bigger sample of 22 galaxies with ALMA data at redshift 1 to 1.5 to look at, to search for potential extended cold gas reservoir around these galaxies. And while I was looking through this sample, so looking at the individual galaxies of this sample, I stumbled on this complex and interesting system. So this is Matilda, or part of it, because what I'm showing here is the HST image. So you see this nice HST image of a redshift 1.17 star-forming galaxy with a nice morphology. If you only have access to this image, you see that there is nice star formation ongoing at the core of the galaxy, maybe also on the corner left of that galaxy. And if you're observant, you might see some residual emission going up north to the galaxy. And so, I don't know, you might wonder, is that the tail of the galaxy? Is it some residual due to the rotation of the galaxy? But if you're lucky like I was, you can put on your ALMA glasses and access the CO emission. And so there are CO 2-to-1 observations of that same galaxy. And as CO traces the molecular gas, which eventually can collapse and form more stars, we can expect this CO emission to show where we saw the HST galaxy, right? So this is what I'm going to show you here. I'm going to walk you through the ALMA cube, so in the velocity space, and I marked with a cross where the HST galaxy is. And so if you follow this, you might start to see that the CO emission, the CO 2-to-1 emission, doesn't only show where you expect it to see. So it seems that the CO 2-to-1 emission is more complex than what we can expect from the HST image. And so could there be another galaxy maybe? And so the natural next step after looking at the cube is to collapse the cube and look at the moment zero map, so the intensity map. So this is what I'm showing you here. This is the CO 2-to-1 intensity map with the contours starting at 3 sigma. And immediately what you see is that the CO 2-to-1 emission is clearly disturbed. You have this weird morphology. This is actually what triggered my interest. And this is characteristic of galaxy mergers. And now, if I overlay these contours on top of the HST image, this is what I'm showing here, you see that not only the CO 2-to-1 emission is disturbed, it's also extended. And so we start to see that indeed we are covering maybe more than one galaxy. And additionally, we also have CO 5-to-4 observations. And so if we repeat the same exercise, now I'm showing you the CO 5-to-4 contours on top of the CO 2-to-1 contours on top of the HST image. And you see again this not as disturbed, but definitely a bit extended morphology of the CO 5-to-4. And both the CO 5-to-4 and CO 2-to-1 peak exactly where we don't see much in HST. So it seems clear now that we are actually looking at two galaxies. Just one of them is very obscured in HST. And indeed, from the CO 5-to-4, we can derive the dust continuum. This is what I'm showing you here, the contours of the dust continuum, and the dust peaks exactly where we are blind in HST. So now it's clear there is a system there. And so now that it's clear that there's a system there, we can look deeper into the baryonic properties of the individual components that make up this system. And so, as I was saying, the CO 2-to-1 or CO in general traces the molecular gas. So I can use this CO 2-to-1 emission to derive the molecular gas. And the way I do it is the following. So I draw a big aperture around the entire system, so around all the CO 2-to-1 contours. I can extract the corresponding spectrum from the cube. And then I can draw a smaller aperture centered on the peak in the northern component and extract the corresponding spectrum from there. So this is what I'm showing you here. You have the CO 2-to-1 flux density spectrum of the entire system on the left. So if you take the big aperture, then in the center now is the corresponding CO 2-to-1 flux density only for the smaller aperture centered on the northern component. So you see these two very nice lines. You can fit them with a Gaussian and extract the integrated flux from there. And so I have the integrated flux of my entire system, the integrated flux of only the northern component. So if I subtract the northern component to the entire system, I get the integrated flux of the southern component. And from there, I can apply the common CO 2-to-1 luminosity conversion to molecular gas mass. that, for example, Gayatri explained yesterday during her talk. So I take the typical star-forming galaxy alpha CO conversion factor for for various star-forming galaxies of 3.68, and I find the following molecular gas mass for the individual components. So the molecular gas mass for the two components is of 10 to the 11 solar masses, and so we're targeting massive galaxies at this redshift, and the molecular gas masses are similar for the two components. So we are indeed looking at the major merger. I would also like to point out on this slide the full width half maximum of the lines that I'm showing here, because if you look carefully, they are of around 600 to 800 kilometers per second. So we are looking at big lines. So we are really tracing a lot of gas here. And so Matilda is a very rich system. So to conclude on Matilda, Matilda is a perfect example of how critical it is to have multi-wavelength data to get the full picture of the evolution of galaxies. And indeed, if it wasn't for ALMA, we would have completely missed this system that is very rich and complex, and that was misclassified as a non-merger. And so the natural question that follows from this example is how common are cases like Matilda at different redshifts? Because, for example, if we take a look at like the work that Ivanna, not me, obviously, the other one, presented yesterday, we see that there's a lot of dust at higher redshift, at redshift above 6, for example, for the work that she presented. So we can expect that there are a lot of systems that are dust obscured, but it's not very clear how common it is to have a system like Matilda at lower redshift, so after cosmic noon. So yeah, so this is important. And if I show you this plot again that I showed at the beginning, so the fraction of major mergers, yes, the fraction of major mergers as a function of redshift, we can expect that this plot would somewhat look different, right? If we were to take into account all the dust obscured major mergers that we simply don't see based on the visual inspection of optical and near-infrared data. So this example really highlights the need for more effort in the direction of using observations that can identify dusty mergers if we want to improve our understanding of the evolution of galaxies. So I'm going to finish on what is next with this system, because this is still ongoing work. And so, as I was saying, this is a rich system, and that's because we can do many things with just that one system. And so I showed you two CO transitions. So I can use these two different CO transitions, compare them, and see how the merger is affecting the ISM conditions of the two galaxies, see if it's affecting them in a different way or not. Secondly, Matilda lies in the cosmos field, so there are plenty of observations at different wavelengths with different instruments. So this will enable me to perform SED fitting to derive other key fundamental baryonic properties for the evolution of galaxies, such as the stellar mass and the star formation rate of the individual components. And I would like to point out here the Spitzer data that you see in the middle row and in the bottom left. I show in green the contours of the HST image again, and you see here that it's almost impossible to distinguish the two galaxies. They are completely blended together, but thanks to the work of Fabrizio Gentile, based in Bologna, who developed a code called FIBO, we can disentangle these two galaxies, and so we can get the individual photometry of the two components. So I thank him for that, because he's saving me a lot of time and effort, and I invite you to follow his talk later this morning. And finally, I am the PI of an accepted extruder proposal to measure the metallicity of the bigger sample that Matilda is part of. And so this will give me clues on the impact of mergers on the metal content of such a system. Yeah, so that's it for me. Thank you for listening to me, and I welcome questions and comments.
Thank you, Anna, for the really nice talk. Are there any questions? Okay, let's start from Romana. No, this is not a recent hand, sorry. Okay, so there are no questions. So I have a question. Okay, no, Sebastian.
Oh, great, Ivanna, thank you for your very nice talk. I just have a very quick question about the astrometry. So when you compare the position of ALMA and HST,
Yes.
do you have any comment on the astrometry of the HST? We heard before in the week that there could be some
yes, some like how it's called, offsets, you mean, between the ALMA data and the HST? Yes, I did not check that, and I was thinking about it recently.
Because that would be very critical for the interpretation of the measures.
Yes, right? Yeah, it's true. So I thought of it. Like, of course, you could wonder if this is just an offset between the ALMA data and the HST data. But I think that given the fact that this is so extended, even if there was an offset, we would still clearly see another, I think, another galaxy from there. Also, given how broad the lines are, I think this points to two galaxies. But I can check, because this is still important.
You say that was in a cosmos field?
Yes, it is in the
suppose that
and also yes, also of course there's this, like, if you look at the Vista data, Ultra Vista data, you see two peaks.
This was more like a general question, comment on people when we combine optical and radio images.
Yes.
But yeah, thank you very much.
Thanks.
Abhishi?
Yeah, thank you for the great talk. This seems like a really interesting target. I might have missed it in your talk, but do you have the optical spectrum for this source?
You mean with HST?
Yeah.
No.
Yeah, I was just wondering whether do you see any AGN signatures for this?
Oh, no, I didn't look into this. I will look into it.
Yeah, thank you. Yeah, it would be great to see if the source shows any kind of AGN activity, or whether there's some kind of
which could be given how massive they are, right?
Mm-hmm.
Okay, I have just a little question. Did you see also the velocity map, the moment one map, or did you show it? Maybe I missed it.
No, I didn't show it, and I didn't compute it, so I didn't see it, but I can look at it. Yeah, so I looked at in the cube, I was looking at extracting the spectrum at different location, so not taking an aperture, but just pointing. And I think we can see the beginning of what could be a rotation of this obscured galaxy up there. But it's not a clear trend, but I can look at the moment one map. Yeah, maybe that could help.
Okay, we have time for another question from the chat from Marika. Thanks for the nice talk. Maybe I have missed the point, but do you also see this secondary component for other CO lines? I don't know if Marika wants to.
Wait, can you repeat the question?
Yes. Do you also see this secondary component for other CO lines? I don't know which secondary.
I'm not sure to understand. Do I see other CO lines than the CO2-1 and CO524, or is it, do I see CO2-1 and CO524 for the two galaxies? I'm not sure. So if it's the first question, I don't have other CO2 lines and CO2-1 and CO524. If it's the second question, well, here, so it's not resolved, the ALMA data. So what I'm showing here is the CO2-1 or CO524 covering the two galaxies.
Okay. Thank you very much.